Yes, thank you. So good morning, everyone. So do you hear me well?
Yes, we can. Loud and
Okay,
clear.
very good.
Perfect.
Excellent. So I have to start apologizing because I wasn't able to make it to Germany for the meeting because I had previously engaged with another conference. So I'm currently sitting in my hotel room in Poland, near to the conference venue where I will join later on. I've been enjoying very much the presentations of this morning. I even have participated in some of the previous projects. But today I am just going to show you what was the outcome of our project, funded by the Horizon 2020 by the CBEJU. And it was so it's actually the second project that I coordinate on biopackaging activities or on let's say organic recyclable packaging strategies. The first one finished about 1 year ago, and usable packaging finished around the end of last year. So we are just recently finished. So the title of the project was called Usable Packaging, and what we wanted to do in this project, as I think many of the other projects that were presented this morning, was trying to really mimic existing benchmarks today in the market of packaging, and propose proof of concepts that would be let's say able to replace the existing ones, which are mostly petroleum derived or entirely petroleum derived along the way. So, well, yeah, these are the highlights of the project. So we basically wanted to start with the bio-waste. So it is clearly a project that is framed within this biocircular economy strategy that is one of the, let's say, big challenges of the EU. As a potential solution to really deal with this very large issue that we have related to the traditional plastics derived from petroleum accumulation, and that they will linger around for many years, up to 400 years in the oceans or in our environment. So we wanted, within this strategy of biocircular economy, close the circle in a way that we would be using industrial bio-wastes coming from the food industry, transform them into a bunch of materials, and combine these materials with other existing bio-derived or bio-based solutions that are out there, so that in the end they would be able to produce a variety of packaging solutions. And of course, the main material that we have been using has been mentioned before this morning. It was PHA. We were aiming, as I said, at developing new grades of PHA. The commercial grades of PHA today are tremendously rigid, and they cannot be applied, let's say, as they can as a monomaterial. At least not in solutions that do not involve genetically modified microorganisms. So our intention was use this technology of microbial mixed cultures that I think is one of the flagships technologies that have been developed for many years and across different projects. At least I have participated in the development of these materials for more than 15 years. And so the aim was to develop one or two, let's say, new grades of PHAs that would have a better viscoelasticity, better viscoelastic properties, better, let's say, flexibility, so that we could combine them with existing other materials and provide these novel solutions. Right, so The partners that were participating, as in this typical structure of projects, are based on large corporations that are actually challenging us with some of their existing, let's say, packaging benchmarks or solutions or proposals or materials that they are in the market, and that they are looking into how to replace with more sustainable solutions. And that was, let's say, we took the challenge from each of these large companies. So the people who actually developed the technologies were SMEs, and also supported by a number of research institutes and universities. So in total, around 25 partners from 10 different EU countries. And the CSIC coordinated the whole effort. So the typical management structure of the project was also used in our project, where there is the coordinator, there is a steering committee, strategic and general assembly, but then well, we also had an advisory board composed of companies that were not involved in the project, but they were, let's say, providing guidance and consultancy. And we also have a stakeholders platform that was extremely useful along the way, because they were actually judging the activities of the project from the outside. So the strategic orientation that the project took was based on the proposal that was made by CBJU program in 2018, which was develop innovative bio-based products to identify market applications. And then we cover all these activities of developing bio-based products, disruptive technologies that would allow them to show the properties that would be required for the replacement, and develop a fully integrated vertical supply chain so that the whole thing can actually work. So the objectives of the project was, as I mentioned, the creation of portfolio, a toolbox of biopackaging solutions for a number of packaging, let's say, applications, not only in food, but also in pharma and even clothing, bagging, etc. So the idea was to develop these biopackaging solutions with a very clear end-of-life scenarios, considering as the main option organic recycling, but also making sure that if some of this packaging was not being, let's say, industrially compostable and eventually or accidentally would end up in the environment, that we would be able to know what would be the degrading times, etc. And ideally, those materials would even comply with existing standards in, for instance, marine biodegradation, etc. So that was, this is one of the main characteristics of PHA polymers. They are extremely biodegradable in the environment, and we wanted to take advantage of this particularity to make sure that that was the case, and we did so within the project. Additionally, the definition of a completely new vertically integrated circular value chain. We develop solutions to optimize the performance or to tailor the performance of these PHA materials to basically match, as I was mentioning before, the requirements for the end users, in this case, the large industries involved in the project. Optimization of the process transformation for allowing these new grades of PHA into these packaging solutions, the development of additional missing elements, for instance, to combine different materials, like generation of multi-layers, where you would require those layers, those different layers to adhere to one another. So we develop also bioadhesive layers based 100% on PHA, with the intention again to replace this missing link that we identified, that the industry identified that was there, just to make sure that different materials can actually work together. Of course, we, as in many projects, we were interested in understanding what is the environmental footprint of what we were doing, and trying to keep this in terms of carbon dioxide emissions as low as possible, and to the extent possible outperforming the today existing materials of the ones in the market today. The work package workflow is very typical as well. So in work package 1, we defined together with the large industries what would be their, let's say, favorable challenges for us to target in terms of selecting applications, but also product specifications. Then work package 2 would just, and not only that, some of the large industries also contributed with their bio-waste is. Some of them were food producers, like Barilla, for instance, etc. And we use reground pasta as so the residues of making pasta as feedstock for the production of these new PHAs. In work package 2 was a very much university and SME driven, where these different, let's say, feedstocks, bio-wastes, were used to optimize the production of different PHAs, and in fact targeted a specific PHAs compositions that do not exist in the market today. For instance, we were very much interested in achieving a PHA that will show, let's say, the maximum elasticity possible, so that it will have this comonomer composition close to the pseudotectic point, etc. And we succeeded to do that. But we also succeeded in making a medium chain length and long chain length PHAs that do not exist in the market today. And 2 grades were developed and scaled, and used also for the prototypes. At least for 2 of the prototypes, it was used. For the others that were demanding higher quantities of materials, we were not able to, let's say, achieve because the RTL level of the project was relatively low, and the aim, as I said repeatedly along the presentation, was to really come up with proof of concepts. So those PHAs were used together in work package 3 with different additives, with different solutions, with different innovations that universities, research institutes, and SMEs provided, with the idea of optimizing their performance. Work package 4 was able to get this toolbox of materials and technologies and combine them so that we would be able to obtain those prototypes, and also analyze the LCA and the biodegradability. Work package 5 was all about analyzing costs and potential, let's say, commercialization scenarios. And work package 6, dissemination, and work package 7, management. So the chosen prototypes are actually here, all of them, but with the exception of 1. That we were not successful in achieving. It was an injection molding the bottle, detergent bottle, that we were not able to achieve in the project because of the let's say, limitations on the material properties that we achieved with the products developed. We understood at least what was the requirements, and this is an open, let's say, technology that will be tackled separately in additional new projects. But we did succeed in obtaining different POCs for bag-in-box applications, for frozen foods, for packaging of pharmaceuticals, for disposables, reusable disposables, bread packaging, and also woven fiber-based bags for seeds and other applications. And I will just show in a minute some of how did we achieve that. So in terms of, well, the single-use plastic directive was really hard on our project, because eventually consider PHA not a natural polymer. We actually complain a lot. We wrote letters to the European Commission about it, etc. And we got positive feedback from them, but eventually though this material could not be used. So what we were intending to do then, in cooperation with the company that was interested in this particular application, was the development of reusable plates, right? So along the way, we modified the target. It was a moving target because of we didn't know really how the directive was going to hit. Eventually, as I said, was not positive for the application, but in any case, we were successful in achieving this replacement of existing polystyrene plates with very good optical properties, but more importantly, we were able to show that these dishes were able to withstand at least 125 cycles of washing in these washing machines without significant compromise in properties. Overall migration was also met in some of these cases, and we were able to develop different, let's say, formulations containing more or less additives that were also naturally based or of cellulosic origin, coming from wastes, bio-wastes, etc. And yeah, well, so my family has been eating in those plates, in those plates for more than 2 years. We wash them with the rest of the kitchenware, etc., and they're still working finely and doing well there. Then there was this bag-in-box application, which was extremely challenging because it was requiring an oxygen transmission rate, which today is obtained by combining different materials, metallized PET or EVOH, high barrier polymers in general, and low-density polyethylene, etc. So the critical parameter was to obtain an oxygen transmission rate that would be better than 1 cc per square meter per day, and we were successful on that within relatively maintaining the same thickness. It would have to be, of course, sealable, and this was all achieved, and our OTR was in the range of 0.36. So that was very good. In the case of frozen bags, the requirement was sealability, printability, retaining lower thickness, protection, the ability to let's say, produce this skin packaging, so that it would be able to also protect from light, etc. And we were able to achieve that, and on top of it, we provided antimicrobial properties to it. So it was tested by a supermarket chain in Portugal, Snoeck Group, with the Continent Retail in the group, and yeah, and they were very happy with the performance of the material. Nest and tube pharma trays were also developed by injection molding, and that was extremely, let's say, amazing how the team involved to develop this application was able to match the mechanical performance of the today existing product based on polypropylene. Even the shrinkage performance was even lower than the existing one, and it was the large company was very pleased, and they said that the material processed very well, and they would see no issue with using it into their conventional injection molding machines. Over 225 pieces were produced. Of course, in this case, we could not use the polymer derived in the project because they had to use 100 kilo. It was a 100 kilo application. In the case of woven bags, it was also a POC developed. It was very challenging because we did not expect the difficulty, so we had to really modify even the structure. We had to implement or incorporate other partners that were not initially devised in the proposal to be able to generate filaments and wave them, so that, but eventually, yeah, even though we were not able to produce a complete pack, we proved the concept, and that was also successful, thanks to the effort and the ability of the consortium to get flexible before adversity, before the problems are encountered. Not to mention, of course, that we, as many of probably the other projects were involved, were hit by this the COVID-19 pandemia, and of course we had to really work magic things here to be able to overcome some of the challenges that were created by this unique scenario. We were also able to develop bread bags. In this case, it was all made with the PHA that was developed coming from reground pasta. So it was a completely circular scenario where the residues of making pasta would be used to actually making the packaging that eventually can be used for protecting bread. The challenge there was to get the water vapor transmission rate that is relevant. We combined really a disruptive technology with let's say a challenging lamination and field blowing strategies, and we were able to achieve at least for the bread bag the barrier properties that were required, and the mechanical performance was acceptable, etc. Sealability, and on top of that, we were also generating two prototypes, one of them with antimicrobial properties and the other one without, with an antimicrobial and antioxidant performance. So that would be an additional bonus to what we were challenged with at the beginning of the project. And that was, I would say, one of the most challenging applications that we targeted, and because, yeah, there was this disruptive technology involved that was never used before. So on the overall, there were, out of all of these challenges, as I said, detergent bottles, we were not able to achieve that. We understand now why, and this is going to be the subject of future work. But at least 3 of the prototypes were very clearly showing a more positive LCA than the existing products. For the other ones, there was not enough information or etc., but do not necessarily mean that they will not be able to achieve that. But at least 3 of them were very clearly showing a more positive LCA. In terms of end-of-life testing, we did test the biodegradation under different conditions, not only, let's say, the organic recycling strategy that would be industrial composting, but also soil and marine biodegradation. And yeah, this is just one example, but many of them passed, or some of them passed all of the tests that were required. All of them passed the organic recycling in terms of disintegration, biodegradation, and ecotoxicity. And so yeah, so we were very, very pleased to see that. And yeah, and with this, I come to the end of my talk. Thank you very much for your attention, and maybe I would be able to answer some of your questions if I have the expertise for it. Otherwise, I'll just direct it to the right partner. Thank you.
Thank you, Jose. So it was very nice hearing this kind of overview about your project and where you started and when you land. I would like to check if there is any question in the room and online. I'm keeping an eye. Otherwise, I would like to ask you the same questions that I was asking Marta. How did you try to connect to your stakeholders here? So we're talking about engaging with the industry. Some of them, they were in the consortium. But did you find other ways to reach out a bit broadly? Maybe can you elaborate on this a bit?
Yes, sure. Yeah. So we have a partner, which is the director of the BBIA, the Bio-Based Industries Association, highly networked. So he was able to pull up, I think about over 100 outside,
yes.
yeah, outside partners in the project. Some of them, and we organize meetings with them, coinciding with our project meetings. Some of them were physically, some of them were remotely connected. But in many cases, there was a reasonable attendance, and we really benefited a lot from that. In fact, our last meeting was done in a trade show in Ecomondo, which is one of the biggest fair for sustainability in the world. And that was also helping the dissemination of the project, because many of the people attending already by default, let's say this trade show, were interested in the project. They attended, they made their comments, and they gave us suggestions all along. So I would say that this is one of the things that the project did very well, thanks to these activities of the president of BBIA.
Excellent. I have another question related to the legacy of this project. So I know you have been coordinating another project before. And so sometimes we are brought to think in 5 years from now, what is the main achievement of this project? Think about the future, think about 5 years from now. What is left here as a legacy from your project?
Well, as I was mentioning before, I think we have proven that we have been able to achieve success in obtaining the benchmark properties. The legislation scenario has been the challenge, let's say. So we started in the project in these disposable applications. Then the single-use directive was really not clearly understood by the consortium. We even complain about it. We look at the future now, and we see the horizon coming from with the new directive of the 2030 for packaging, where everything has to be recyclable, whether let's say biodegradable or not. We also do not share this vision, because we think that the strategy that is more sustainable is not the mechanical recycling, but the organic recycling. So you cannot really try to, let's say, recycle mechanically something that is designed to be converted into carbon and brought back to the soil. So these are, I would say, the most challenging scenarios, the legislation, and that is what is more worrisome by discussing this with the large industries, because they do not see how, if they invest on this, how the outcome will be for them, and whether those materials eventually will be allowed to be used, etc. So there's a lot of uncertainty. I would not say it's technical. There are some technical challenges still, but they are more related to how the legislation will shape up in the next few years.
Thank you. This is very interesting. I think I will pick up some of these messages also for the proceedings of this meeting. But I see that there is a technical question in the chat from Salvatore, and he's asking about what is the scale of PHA production reached in your project?
So in the first project that I did, that I coordinated, it was it was an innovation action. So we actually handled 5 tons of bio-based materials. In this project was more developing at a relatively low RTL, and we did create a pilot plant for that, not only for the production, but also the purification. There were 2 pilot plants that were established and that were tested and checked. And those were in the range of maybe 100 to 200 kilos a month. So it's relatively slow, but it's relatively low capacity today, but scalability is just a matter of investment. So it has been proven that can be scaled at the both challenging processes, which is the fermentation and the purification.
Excellent. I think this is, there is another question. So I hope that Salvatore is happy with your reply. And there is another question from Aman. How do your grades compare to other medium and long chain lengths available by Danimer or Kaneka, such as hydroxy ixanoates? Okay, so we generated those polymers that I will describe in a minute, using this technology of microbial mixed cultures, which is supposed to be a low-cost option, where the microbes actually they create this population that in a way self-organize, but they are naturally, grown in their ability to produce PHAs. And we generated 2 new grades of PHA containing valerate contents of 35% and 70%. Those materials do not exist in the market today. They have improved elasticity. They are based on medium chain length. They derive from bio-waste, which is not the case for existing, long chain PHAs, where either they are produced outside of Europe to start with, but also based on GMOs, etc. So those materials have the potential to achieve a lower cost. Within another project in which I have participated that was finished about 3-4 years ago, we also use urban residues, urban waste, like a sludge and the organic fraction of the municipal waste. So eventually, those materials in the calculations were able to achieve costs below €1 per kilo, which is today the cost of polyolefins, etc. So this technology of microbial mixed cultures is unique to us, to Europe, and it's being developed along different projects, and they definitely generate materials that have properties that have not been seen and do not exist today. I think Aman is also happy. Yes, great work. Thank you so much. So you can read the reply. I would like to wrap this up now with you, Jose. So thank you so much for your contribution. And now we take the conversation to Willem. So
welcome. Good afternoon, everyone. So I'm Willem Uyttendaele, and I will give a short talk about the Preserve project. So the goal of this project is to develop high-performance, bio-based, sustainable, and recyclable packaging. So for this presentation, I will start off very quickly talking about Centexbel, the company I work for, who we are, what we do. Then continue with the Preserve project, the goal of the project, and then go into some of the activities that we performed within this project before ending with some final take-home messages. So then regarding Centexbel, so who are we? So we're a Belgian collective research center and technical center for the textiles and the plastics converting industry. We have about 180 employees spread over 3 sites within Belgium. And we are equipped on the one hand with a range of different testing laboratories for physical testing, chemical testing, fire testing, and antimicrobial testing. So one example from these testing labs is, for example, certification of the mouth masks that you have all come to know and maybe love as well. This is just one example of what we do. And then the second part of the testing is also some pilot platforms. And this is then mainly for research and development regarding extrusion of novel materials, making novel types of textiles, and also coating and finishing applications. Now then for Preserve. So the reason we started with Preserve is because there is some kind of a need for high performance bio-based packaging to meet the European sustainability goals. But in order to achieve this, we need to do a few things. And first of all, we need to enhance the properties of some of these bio-based packaging materials to meet with the current industry standards. We also need to look at how we can recycle and recover these bio-based materials, because of course it's very nice if we can make everything out of PLA, PHA, or some other alternative, but if in the end we can't recycle it, then what are we doing? And then finally looking at also at upcycling of some secondary raw materials. So mainly if we look at food materials, if we end up with some blends of different polymers, how can we recycle them or even upcycle them into different materials? And then concretely for the project, we have a few demonstrators that we work towards. So on the one hand, there is some food packaging related demonstrators. Examples of these are a flow pack or some beverage cups, some beverage bricks that can be used for all kinds of drinks or food applications. And then the second half is more related to the recyclability and the upcycling strategies. And the goal here is to develop different types of carrier boxes, injected jars for example, cosmetic applications, and so on, using these recycled materials. Of course, this is something we don't do on our own, so there is a whole heap of partners working on this project, and it's coordinated by Iris Technology Solutions. So now then for some of the activities that we performed at Centexbel regarding this project. So first of all, the upcycling. So the aim of this project, there is a very big scheme on the material flow throughout different demonstrators, throughout different applications. But I will want you to focus on the center highlighted in orange, where we saw some strategies related to delamination of multi-layer structures, self-reinforcement to look at how we can improve the properties of different polymer blends, and then also looking into enzymatic recycling. So looking at using enzymes to improve the recyclability or improve the biodegradation of different materials. So first of all, when we look at some self-reinforced materials, so the goal here is to look at what happens if we blend different materials that are supposed to be immiscible. So an example here is using a high fraction of low density polyethylene and actually blend this with a very small fraction of polyamide. And if we do this properly in a film extrusion, we will see that the polyamide will form these kind of microfibril structures within the film itself. So you will see in the machine direction, they are really elongated, and you get some kind of a composite material made from a matrix of polyethylene and then a reinforcement of polyamides. And this resulted in an increase of 10% in the modulus and an increase of 10 to 100% in tensile strength, thanks to the addition of the small fraction of polyamide. Now then, another thing we investigated is looking at self-reinforced PLA. So this is something we have been doing at Centexbel quite a long time already, more in composite applications, but now we are looking also what happens if, for example, we have a waste stream of PLA and we want to improve the properties of this material so that it can be used a few more times. And in that sense, it's interesting to look at self-reinforced PLA. So the goal here is that you work with a low melting and a high melting point PLA, and by blending these, processing these at the right temperature, you once again get these microfibrillar structures, as that you saw in the last picture. But this time, instead of using polyethylene and polyamide, we use a low melting PLA and a high melting PLA to get these kind of self-reinforced structures. And here we see an increase of about 25% in modulus for these self-reinforced blends compared to just the virgin PLA. And then finally, for the recyclability aspect, we also looked at the home compostability of PLA. And the aim here was to add an enzymatic master batch developed by Carbiolise into PLA and see the effect of this master batch on the biodegradation under home compostability conditions. So a first assessment was already made with the first batch, and there we saw that most of the enzymes degraded during the extrusion process. However, with the second batch, this was completely solved, so we were able to extrude a PLA containing this enzymatic master batch. And what you see here on the slide is a first screening that Carbiolise performed regarding depolymerization. So you see the reference PLA on the bottom in blue almost does not depolymerize under these conditions, while addition of about 5% of this master batch drastically increases the speed of depolymerization. These samples as well are now also submitted for home compostability tests, but the evaluation of these materials under home compostability is still ongoing. Then the second aspect that we performed at Centexbel is related to coating activities, and then more specifically coating of PHA. So the goal here is or how we came up with this is how can we make kind of traditional polyethylene paperboard packaging, how can we make this easier to recycle? And also, can we switch to more bio-based solutions? So can we replace this polyethylene by a bio-based material? And in this sense, PHA is quite an interesting material because also already from articles, it's known that it can have quite good water vapor transmission rate barrier properties. So in that sense, it's very interesting to look for PHA for these kind of bricks, cups, trays, etc. As in a barrier layer. So maybe a little bit of background. I know it has been explained a lot already on PHA, so I will go over it quickly. But essentially, PHA is a bacterial polymer that is made in high. If these bacteria are in an environment with a lot of carbs, but not a lot of nutrients. And in that sense, they will store these carbs as some kind of an internal fat layer in the shape of these PHA polymers. What is quite interesting about them is that they are on the one hand thermoplastic, which allows quite a lot of processing on them, and also that there is quite a lot of variation in PHAs. So a PHA is not one specific polymer, it's more a group. So for example, like you have a large array of polyolefins, like polyethylene, polypropylene, and so on. You also have a large array of PHAs. And as I mentioned, they are quite promising due to their barrier properties. And they are not only bio-based, they are biodegradable in a range of environments. They are recyclable and they are even biocompatible. So quite an interesting product. The issue, however, is how do we turn this PHA powder pellets, how do we turn it into an actual nice and homogeneous barrier coating? For this, we took inspiration from the PVC sector, where they use something called a plastisol. In that sense, they mix a thermoplastic powder and a plasticizer. They mix this together, they heat it, the plasticizer is absorbed by the thermoplastic powder and it gels into some kind of a homogeneous coating that you know. So we tried the same approach. It worked for PLA, it works for PHA, and also optionally we sometimes include some water and processing additives to make sure that the coating behavior and the flow of these materials is to what is needed. Now then, for some of the properties and the details, so this PHA coating is applicable on paperboard. That is, of course, quite important for this project. We are able to fuse this material into a coating by heating it for only 2 minutes. So this solves a lot of the thermal degradation issues that PHA has, because only with 2 minutes we can obtain a nice and homogeneous layer. Since we're working with food contact materials, all the components that we use within this PHA-based coating are all food contact approved. And initial evaluations show that this coating fully disintegrates after only 29 days. Now then, for some of the properties, since we are working with food, and I mentioned plasticizer, some of you might be thinking, but what about plasticizer migration? It's quite an important aspect, and it's something we did a lot of screenings about. But this is some of a summary of the results. So what we tested is we tested how the plasticizer migrates onto an absorbent material at elevated temperature and under the pressure of some weight. And you see that for some plasticizers, for example, plasticizer 2, after a day or after 2 days, 16% of our plasticizer has migrated out, which is a whole lot and definitely not acceptable. However, if we switch to different plasticizers and different plasticizer blends, this goes to well below 1%. Then for the barrier properties, so one of the properties we started measuring is the COP test. This determines in what way water gets absorbed into the paperboard. So the less water absorbed, the better. And we see that for the reference paperboard on the left, this absorbs about 25 grams of water per square meter in 2 minutes. While for our PHA coatings, we are at a value of about 1.1 grams, which is actually quite similar to some commercial wax-based solutions that can already be used for these kind of packaging materials. Then for the other barrier properties, what is also important is the water vapor transmission rate. And here we compared some PHA foils and also PHA coatings under different conditions. And what we see is that for some of the latest developments, we get a water vapor transmission rate of about 70 grams per square meter per day. And since about 2 days ago, we got some better results, and we actually got this down to about 30 grams per square meter per day at 38 degrees. This is not quite yet what is expected from the industrial partners within the Preserve project, but we are about a factor 4 or 5 away at the moment. So we hope to achieve this within the next 2 years that the project is still running. So then finally, some take-home messages. So first of all, as I mentioned, it's possible to improve the compostability of PLA using these enzymated master batches. It's also possible to self-reinforce blends of recycled PLA or blends of recycled PE with polyamide to improve their properties. PHA also shows quite new and interesting potential as a barrier coating for food packaging. But it's something we will still have to work on to really get it market ready. So to anyone here, if you're interested to follow more about the Preserve project, you can go to the link on the slide, to the website to subscribe to the newsletter to really follow the further developments. And with that, I would like to thank you for your attention. If you have any questions, please ask them now or feel free to send me an email.
So, yeah, let's go ahead.
Thanks for the presentation. I have a question regarding the PHA covered cup or other packaging.
Yes.
Have you already performed tests in paper recycling? How does the PHA behave in contrast to wax or polyethylene?
No, indeed, very good question. So it's planned within the project to do tests regarding paper recyclability. And actually, since last week, about 1 kilo of these PHA coatings has been submitted to a certified recyclability plant to assess this.
There is a question online. Aman is asking, have you done an aging study on these coatings? And if yes, are they stable, especially in the presence of water and heat? He is assuming that coating is done at high temperature above melting point.
Yes, so the coating application is done at high temperature. So to gel this PHA at the moment, we need about 170 degrees. But when it comes to the stability of the PHA, this is something we haven't tested in the packaging. But since we're a textile institute, we also investigated the use of PHA as artificial leather. And in that sense, we did some outdoors UV testing, weathering testing, simply on the roof. And after a month, there was only minimal damage to this PHA artificial leather. So to some extent, there is the PHA coating is quite stable.
Hello, good morning to everybody. I am Francesca Braca from ARCHA. Just a brief introduction. I am an European project manager in ARCHA, and ARCHA, my company, is a chemical and biological laboratory, but also a research center for the development of European, but also national and regional research projects on different fields, let's say, but mainly in the environmental field for application of, for example, the evaluation of the sustainability of the end-of-life validation of some products, even packaging, as we performed within MANDALA project, which is already presented by Marta, our coordinator in MANDALA. But I'd like to focus this presentation on the final validation of this packaging, and also for the sustainability assessment. As you already heard from Marta, the project is in the final months, but we are running to achieve all the final results. And these are, let's say, not the last final results, but the almost final, since several, let's say, validation are still running. And I explain what. So okay, sorry. Okay, just to focus our attention on the on this final validation of the developed packaging, since, as I said, ARCHA has been involved especially for the end of life. And so for the study of the performances of this multi-layer packaging, to see if they are especially biodegradable and compostable, and as you can see, in several environments. We also performed the validation for the life cycle assessment and the life cycle costing, achieving and collecting the information to evaluate the impact, both for environmental and economic points of view. And just to answer to a previous question from Chiara, in terms of the social acceptance of this new material coming from stakeholders, also common people, we provided also a survey to evaluate this social point of view and to see if people is, let's say, positive or less or negative towards the sustainable packaging. So, okay, our main pillar that we need to focus as ARCHA point of view, let's say, ARCHA activities, where the evaluation of the sustainability, especially for the eco-design of the packaging at the beginning of the project. And This was performed thanks to another partner that was involved in this, especially part of eco-design. The reduction of the fossil-based materials, and both this activity and all the developments during the project were validated through the life cycle studies in terms of environmental and economic point of view. The second pillar was the evaluation of the end-of-life options. So we, as Marta already said, developed mainly 3 formulations. One of them was by using already biodegradable material, combined with a new formulation to assure and to provide the specific performances for the conservation of the specific food, for the also recycling performance. So we need to consider both these aspects in terms of compostability and recyclability. And I will provide you the results for the compostability. And in addition, we validate all the new processes in terms of the guarantee of the health and safety for workers. This is, let's say, very important from our point of view to assure that all the new processes are not dangerous, hazardous for workers, since we are using new materials, new chemicals, let's say different condition as usual, perhaps, but we needed to demonstrate it, we don't know. And we needed to evaluate if during the process, the application process, so it means the lamination, but also the delamination process, some, let's say, dangerous chemicals can be produced for the specific conditions, for the specific application that we have. And this part is going to be finalized in this week, let's say, so I cannot show you the results. But till now, we, let's say, obtain already all the concentration of the chemicals that can be produced compliant with the limits for the regulation, for the health and safety regulation. This means that there is no specific risk for workers that are working in this new process. Sorry. Okay. So we let's say provided that we produced 2 different demonstrators, as Marta already said, one for food application and one for pharma application. What I'm going to describe you is the food one, which has the specific biodegradable, let's say, and compostable formulations. Obviously, the pharma formulation has also the aluminum as foil for the cover of the packaging. So we didn't perform the biodegradation and compostability on this material. We compare to evaluate the final sustainability of these products, a reference, a benchmark material that is the traditional film already on the market, and we compare this with the new formulation that we developed during the project. And this validation was done on all the 3 pillars. Something is still ongoing, as I said, and something is already achieved, but we needed to wait to the end of the project. Let's see. The goal of this validation was to assess the environmental and economic impacts of the our product, and we performed this with the comparison of the traditional product with the new MANDALA 1. We used it as functional unit 1 demonstrator. We consider, this is since some data were not, let's say, on the same scale, on the same dimension, and so we needed to compare the raw material used for the Mandala product and the benchmark one, and their end of life. So their grave, let's say. This is due, as I said, still for the benchmark product. As you can imagine, we have the industrial data coming from all the production, all the film, let's say, extrusion, or what is needed for the process. Instead of for the Mandala one, we reached the TRL 5, so we have only the pilot scale production. And this is important not to compare this very different dimension for this production. On the other side, we performed, and we are, let's say, including in our final study, the lamination and the lamination processes, since these are the new one, and we need to understand the amount of the impact due to these new processes. The first results for the environmental point of view, as you can see, starting from the raw materials, you can see Mandala demonstrator is on your left and the benchmark is on your right. We have the column for the raw materials impact and the end of life as final option, let's say. The Mandala food demonstrator was addressed to the composting plant, and the benchmark to the, let's say, average end of life option for the no biodegradable, no recyclable plastic, so incineration and landfill. And as you can see, the raw material production is bigger for the Mandala demonstrator, even if not a lot, let's say, more or less 25% more. Instead, the end of life option is obviously, let's say, lower for the Mandala food demonstrator than the benchmark one. So we need to balance this impact by considering their production processes. About the cost impact, as you can see, the cost of the raw material is higher for biodegradable and compostable plastics, as already discussed even from the previous speakers. These materials are more expensive than the traditional ones. So we needed to consider this, but we needed to evaluate that this material can provide, let's say, benefit for the environment. So we needed to, let's say, to increase their production, to reduce their cost, as it is obvious, but taking into consideration that the end of life is more sustainable. It is true. Then we performed the validation for the end of life option, and we applied all the standard method defined in the N13432 to evaluate and to comply with the requirements for packaging recovery under composting and biodegradation. In particular, for the final demonstrators, we verify and we comply with the industrial compostability conditions for all the parameters and requirements under industrial composting conditions. So for the chemical characteristics, for biodegradation, disintegration, and ecotoxicity. This is this was verified for the film final demonstrator, and we performed also further tests to evaluate the preliminary behavior of the, let's say, biodegradable formulation towards in different environments. For the biodegradability, I don't know if all of you can know this test. We performed the test according to the ISO 14855, and we quantified the CO2 that is produced by the polymer, they use it in formulation, in aerobic conditions by using the determination of this CO2 and quantification of the percentage of biodegradability compared with the organic carbon that is in the polymer. The requirement is that biodegradability has to be more than 90% within 6 months. All this test was performed according to the OK compost industrial scheme that is provided by TÜV Austria. For the disintegration test, we performed the test according to another standard that is important to, let's say, use this standard to assure that our samples, our materials are compliant with the requirements. So we applied the ISO 16929 and we used the pieces of the film inside the compost in an inoculum, and we, let's say, follow all the tests for 12 weeks. At the end, we needed to verify that more than 90% of the initial material is, as dimension, below 2 millimeters by sieving with a sieve with the 2 millimeters of dimension of the holes. More than 90% is below this sieve. And what we obtain more than 90%, about, let's say, 90% at the plateau level after 90 days of industrial biodegradation percentage of the formulation. So this is, sorry, the animation doesn't work. I can go on with the next one. Okay. For biodegradation, it is compliant with the requirement. And for disintegration, the same, since we achieve more or less 99% of material below 2 millimeters as dimension after 12 weeks. In addition, we performed, oh, help me. We performed the ecotoxicity test according to the same standard, and in particular the OECD test 208. We evaluate both germination and plant growth test. Doesn't work. Okay. We evaluate two different seeds for the plants, and all the results that we obtained by comparing the compost after disintegration, coming with the disintegration of the sample, the plastic sample, and a blank compost that has not been in contact with the plastic material, is more than 90%. And also this parameter is compliant with the requirements. So our final demonstrator for food packaging is, let's say, compliant with the certification scheme. So it could be certified according to OK compost industrial protocols. We performed also some preliminary tests on the 4 different environments that we can apply on this plastic material to verify their biodegradability property. And we performed the test in water, fresh water, and we achieved 93–94% after 56 days for the, let's say, preliminary formulation. Without, as you remember from Marta's presentation, we used an adhesive. We didn't test this adhesive in the formulation. In addition, for the home biodegradability percentage, we achieved 92% after almost 250 days. For the marine biodegradability test, we achieved almost 94% after 50 days. This is like a strange result, but we needed to confirm with the final optimization of the formulation. And for the soil biodegradability test, we are still running since we started more than 1 year ago. The test is not finished yet, but we achieve 80% after 1 year. And we need to check when we will achieve, if we will achieve more than 90%. So the conclusion, the bio-based and biodegradable demonstrators from MANDALA has an environmental point of view that is very high due to the raw material used, the raw material production in particular, and this is due also especially for their cost. And this is very impactful compared with the benchmark. On the other side, we achieved and we demonstrated their compliance with the requirements of the biodegradability and compostability under industrial composting condition of the developed final formulation, and let's say in other environments, but we need to confirm them in the, let's say, in the future. I hope in another research project, but we will see. So thank you very much for your attention. And if you have questions, further information.
Microphone, can we go there and use that microphone? Okay, Francesca, I think we're all running out of time in terms of these projects. Everybody's rushing up with test and validation by the end of May. But I was wondering, like, normally after these projects, there is some time to continue a bit of work and testing. So when do you think this kind of final results will be available? Maybe in autumn? Because this is the question. This is the questions that we get when we are at the fair. So when do we see this stuff happening for the
well, it depends.
This up, yeah.
So for the, especially for example, for the LCA and LCC studies, we are collecting, and we has collected several new data, let's say in these days. So I cannot provide you today. As you know, you are all involved in research project. The last months are the most mandatory, but also rich of the results that we need to elaborate and to, let's say, understand better. So if some data you collected, let's say, 1 week ago, you cannot provide in a conference and in official way, let's say. We need to provide the last deliverable at the end of May, as in BioNTop project, I know. So we are finalizing the experimental part, for example, for the health and safety that I not show you, since here we need to comply with some limit, regulation limit. So we need to verify this data very well. We are an accredited laboratory, so we know that each data that you can go on can be critical, so we need to be sure. And the last sampling activity was performed on the end of March for MANDALA project for the health and safety. So we are finalizing the analysis now, I think in 1 or 2 weeks, since the deliverable has to be provided and the technical report as well. For the biodegradability, I can say it depends from the material. It is not our, let's say, possibility to decrease the timing. We are 80%. We can see that the graph is still increasing. So if we have not yet reached the plateau, we still need 1 month, 2 months, 3, but I don't know. I cannot be sure.
So maybe with the final report published of this project, we will get some more insights, like in autumn.
Yeah.
Right.
As I said to the partners that are involved in this project, we will go on even if the project will finish the end of May, since the test has been started 1 year ago, but this test need a lot of passion.
Time, yes.
And so we cannot be, let's say, faster than what the material needs.
Thank you, Francesca. I don't see questions in the chat, but your colleague and competitor.
Yeah, yeah,
I know, just a
but
one
we know
question.
very well.
No, it's only for life cycle assessment.
Okay.
How fair you do find that to compare with the reference materials, which are very well established, have optimized processes, optimized data in these life cycle databases, while you develop something quite new? Do you think the information you got for these materials you obtained in the project is fair to compare? If it's not too severe, yeah, is it?
Well, we
fully
compare the as benchmark, let's say, a material that has the same performance. So you need a multi-layer material compared with the multi-layer material, and the formulation were provided by the expert, not from our side. So we needed to compare the same material for, let's say, the same application. I think that here we needed to be, let's say, we needed to demonstrate and to clarify what we are going to compare. The performances of the benchmark that we considered are the same that for our material, and we wanted to assure these performances. So the data needed to be checked, let's say.
Yeah, it's sometimes hard to compare with well-established materials already. If you have the other way, if the polyethylene would now be invented now, it might be that they would have a much worse LCA than after 60 years of involvement.
Yeah.
Good afternoon, everybody. My name is Verstichel. I will give the next presentation before dinner, before lunch. I think you are all very hungry, but I've seen a lot of interesting projects today already this morning, and which are very well related with the work we are doing and how we feel about compostable and biodegradable examples, materials. So let's try to get to the next slide. These are the topics I will present. Who are we? Where is our company? What is recycling and what is going to be the role of compostability inside that? Some more information, biodegradation, already also nicely expressed by my colleague of ARCHA, and also some EU research projects we are involved. So Normec OWS. Who are we? We are a company founded in 1988. We have 35 years of experience in the field of biodegradation, compostability, and ecotoxicity testing. For this work, we are recognized by certification institutes worldwide, so not only in Europe, but also in America, in Japan, Australia, and we are working on the state-of-the-art activities. Other things we are doing is life cycle sustainable assessments, waste inspection, and also we have an analytic lab. We are recognized for compost analysis by VLACO, the Flemish Institute. Our work is mainly on export. You can see it also from the graph. Everywhere in the world, we have done tests for everybody. Only in Africa, we are missing a little bit, but that should be solved in the near future. We have about 105 employees. Our head office is in Belgium, in Ghent. But we also have a lab in America, in Dayton, Ohio, and we have an affiliate partner in Japan, DGK International. Now, more about recycling and what can be the role of compostability inside of this. You all know, and I think there's more expertise than me, what is food packaging and what can be the benefits. So food packaging can be quite broad. It can be plastics, paperboard, and laminates, but of course that's needed. It has protects the food from contamination. It improves the shelf life of the products, also protect from physical damage, and to keep the freshness of the products. So it's very useful, and we need them to protect everything. But what do we have to do after use? And this is the ladder of Lansing in a little bit different way. The first thing, of course, is to prevent the waste. This already can be done by smart design, not packaging in double packaging prevention. Also, you have to be prepared for reuse, like for shopping bags, you can reuse it in a second roll. But for many applications, this is still not possible, or will not be possible, and then we have to recycle them. And as mentioned before, organic recycling or compostability is at the same level as mechanical and material recycling. even if recycling is not possible, yeah, we have to still landfill of incineration, but this has more negative environmental impact compared to recycling or organic composting. I got this data also from the European Council of Chemicals. They say that more than 85% of the plastic waste in Europe is still incinerated, export of landfill. So we are not really playing a sustainable role there. Now, recycling of plastics can be done on many processes. Conventional plastics typically is now mainly done in mechanical recycling. You recycle the plastics back again, you have it. Often it is a down recycling, and even in the best case, like for the PET bottles, the recycling is limited. So for PET bottles, you say that on an average basis, you can recycle it 3 times before you get too much degradation due to this process. Also, recycling by dissolution is done often, but also in this part, you have to add the original polymer back to have a good product. So keep in mind that it's not completely circular. Chemical recycling, there are the different methods occurring now, and then development. So do the polymerization by pyrolysis and gasification. Then you go back to the recycled monomer or to the recycled feedstock, and you have a more circular approach to finally produce again the plastics. There's an overview of Plastic Europe in 2022. Also, enzymatic recycling is something that's which is now hot and news, but this is still in development. For compostable materials, in fact, you have the same recycling options, but your battery is running low. You have the same options, but it's all a matter of volumes, because like PLA, it can be very well mechanically recycled, also be depolymerized, but the volumes are not big enough now to start with this, to be economically viable and to do this work. Still, they have the advantages, composed materials, that they can also be recycled by organic recycling. They are completely biodegradable, so they have no negative impact on the environment. And when your material is starting materials is bio-based, you have a really circular approach, and that's we've seen in many projects this morning, and it is a true fact. The other advantage is that in Europe, compost facilities are already available, so it's quite easy to start working with, and there are collection strategies already developed and running, so it should be a nice short loop approach to include compost products. Only thing is, then, as mentioned before, like the single-use plastic directive, there's a little bit a miss of chance for these plastics. Yeah, they are not allowed anymore to be used, and maybe there should be a distinction being made that the conventional plastics and our bioplastics, like on PHA-based, that are degradable in many environments, to allow them, or to get them, allow them back again as a single-use material. Might be also an idea to, like, these projects to work together to have a kind of intentional letter that to show that plastics like derived from PHA can have a benefit also as a use as single-use plastic. Nowadays, there's a really shift to paperboards, and that cannot be used anything. But also keep in mind that for paperboards, a lot of chemicals, a lot of biocides are sometimes used. So we are putting that back in the environment, and maybe we are not doing the right thing there. Next, but the role of compostable materials is getting recognized in Europe. They have an AC communication on the EU policy framework for bio-based and biodegradable and compostable plastics, and they see 2 main benefits for this type of materials. The first one is that when they have a higher bio-waste capture, when we get more organic waste into the composting bin, it's a benefit for our environment, for our world. And also when they lower the concentration, the contamination of compost by non-biodegradable plastics. So this like 4 suitable applications with these compostable plastic, these conventional plastics should be replaced by compostable materials. One of them is a fruit and vegetable stickers, which is logic. You can treat it and throw it away immediately together with your food. Tea bags, filter coffee pots, and also very light plastic carrier bags. This is also included now in the proposal for the revision of the EU legislation on packaging and packaging waste. So these 4 materials will be they will have to be compostable in future. But of course, for us, it's not only limited to these materials. There are much more food contact products which are suitable and which will increase the organic waste going to a composting plant. Also, for materials like laminates, blend of plastic, they are hard to recycle. We did a lot of research in our project. I will demonstrate once more that it's really hard, and that organic composting can be a very nice way to treat these different sources of plastics. In Italy, they had a good approach there, and in fact, Italy is a little bit of foreigner in effect. Compost has then been seen as a solution for the soil erosion and also for desertification. That's why they started there with the compostable waste bags. Of course, Novermont was also strong involved in there, and they are a key enabler for more bio-waste collection. So this way, much more waste, organic waste, went into the composting bin, and this was a benefit for the environment. But of course, also other compostable plastics, they see it as an enabler of a solution. This is not as a waste. They help to get more organic waste into the composting bin. It's a different approach, like in Germany, for example. There it's seen plastic as a waste, also composted plastic. How do we have to treat it? And it's not something beneficial they added it. Well, it has a beneficial value. Just some few words on the requirements for industrial compostability. I think it's also explained already by ARCHA. So we have two environmental safety requirements, which is that they should not be having metals or fluorines inside, and it should not be ecotoxicity. For EN 13014-32, you have only to do plant testing and no worm testing, but this is asked for other standards like in Australia. And you have two characteristics for degradation. First of all, you have to demonstrate that your material is fully biodegradable. Really on a chemical level, this carbon of your material should be converted into CO2. And the disintegration should be sufficient that your material is not visually disturbing your compost at the end of the test. Now, let's get a few more words on biodegradation. Biodegradation for us, the only scientific proof and the correct parameter is the conversion of the carbon into CO2. It's not a reduction in molecular weight. It's not a carbonyl index. That can be the first science, but it's not a proof of really final, complete biodegradation. Past levels that should be achieved is 90%. Absolute or relative to a reference material. And here you see a nice graph of the biological pathway for the aerobic degradation. So the carbon of the is converted with the addition of oxygen and microorganisms into CO2, water, residual carbon, and carbon biomass. You can also see that for this lab testing, we only follow up the carbon in the CO2. That's always also the reason why they say that 90% biodegradation is sufficient, as the carbon in the biomass is not considered. And it's often released only very slowly. Still, there is an additional requirement in many standards, not yet in the European one, but components in a material between 1 and 10%, or even in ISO level between 1 and 15%, has to be tested separately for biodegradation. This means that you cannot make any starch-based material anymore with 8% polyethylene. That will not pass this testing. Still possible in effect in Europe, but it should be changed and will be changed. In OECD, which has also guidelines on biodegradation, OECD is mainly for chemicals. There you only have to reach the 60% pass level. But for us, if you have 90% biodegradation, it's a proof of complete biodegradation, and you have no microplastics in the environment that you occurred. So that's beneficial compared to other conventional plastics. Now, biodegradation, there are a lot of opportunities, but these can also be useful in a certain environment where you will submit a material, so in soil, freshwater, and marine conditions. As you can see, a lot of agricultural products are used and will end up in the environment, also nets for protecting your materials. This is also interesting. These are just slow release fertilizers. These are often made, the coating is made of a plastic, and often just plastics that are not degrading. So we're just putting plastics into the fields, into the agriculture zones. So that's not what we want to like. It's logic that these should be degradable, only of course at a slow time to release the nutrients not too fast. Other applications are mulch films. Also, these are not so nice. The urns, plastic for protection of plants. So for these materials, for these applications, biodegradation can be an interesting characteristics. But also non-persistency is an important thing. A lot of materials get into the environment, not that we want to, but just by wearing. You see also shoes, tires, that's problematic. We have a lot of microplastic from textiles coming, as cannot be recycled in a good way also. And of course, that's something smoking is not allowed. It's not good, but you see a lot of cigarette butts in the environment, and they should be degradable. This, of course, due to human behavior, these are not less due to human behavior. And that's a fact we also have to work. The importance of biodegradation is getting more and more recognized in policy and legislation. There's now an EU fertilizer products regulations set up in 2019. And they say that by July 2024, we need to assess the biodegradation criteria for which these fertilizers, like these slow release fertilizers, should be fulfilling. So the goal is to have 90% organic carbon and conversion into CO2, and also the duration is 4 years. They will test it in soil, probably also water conditions are needed to test, but it's still under work going on. Also, the ARCHA has a proposed restriction on targets on intentionally added microplastics. Microplastics are defined as plastics smaller than 5 millimeter. They are not set. They had set this proposal. We were active in this also. The first field is by doing screening biodegradation tests. You have tried a tiered approach according to the OECD guidelines. However, for plastics, but the polymers, they will not fulfill these requirements as it's quite short duration and then only aquatic degradation testing. So we are allowed also to follow the standard ISO procedures like ISO 14855 and then ISO 17955 in soil. And they are now setting this, they have made a proposal. The ARCHA, currently EU is assessing this proposal and are reflecting to start develop the most appropriate measures. So there's work going on in this field. Now, also important to know, environment is an important factor for biodegradation. It's not a material that is compostable, may not be biodegradable in water or in marine conditions or in soil. And there are two main reasons for that. Compost is generally to be considered as the most aggressive environment, certainly industrial composting, because there you have the high temperatures, up to 60, 70 degrees, and you have the presence of a lot of fungi, bacteria, and optimizators. These fungi are often needed to degrade the more recalcitrant materials. Also, they are needed for degradation of lignin, this natural material, but only due to the activity of fungi, they can be degraded. For home composting, you have the lower temperatures, so that's already one reason why the degradation is going on slower. And then soil is less aggressive compared to these two. Main reason is that bacteria are present, but not at that high concentration as in compost, and also the low temperatures. For fresh and marine, there's seems in general to be less aggressive when there is a need of fungi for degradation. As in these environments, fungi are present, but they are not so active as in soil and compost. Landfill is not really a good option in Europe. There's a ban on that, and we agree on that. And also anaerobic digestion, there's a little bit of different behavior. In anaerobic digestion, we have mainly the bacterial activities, but there's another kind of bacteria than in the aerobic processes. Here's some kind of overview of the materials we made with Nova. Also will update it also. In which environment each material will degrade. So cellulose is a natural material, can degrade in any environment. This is the same as by PHB, already discussed from the project before. For PLA, it's interesting, only two environments are considered here. This is industrial composting and thermophilic anaerobic digestion. Why? PLA needs this thermal trigger to start the degradation, start the hydrolysis, and to be completed biodegradable. PBS also not that much, and PCL, yeah, you see mainly in soil and industrial compostable, but depending on the application, on the type, it can also be in water conditions. So all of them, this is not fixed in stone. It's also depending on the molecular weight of your material or other characteristics like crystallinity. So it should still be checked. Now, what some examples of EU research we are involved in and where we show that biodegradation can be a nice issue. This is, of course, the Biodegradable project, for which we like very much, and it had the goal to develop new novel packaging films in textiles. We want to have to be bio-based and also biodegradable at mild conditions. As also mentioned by Raoul, our start material, Raphael, our start material was PLA. Why? It's bio-based, it's biodegradable, and at the moment also mostly affordable, and quite high production capacity is already available. But we know that the PLA needs a thermal trigger before there's to start degradation. And in home compost conditions, you don't have these high temperatures. You only start working at 28 degrees as defined by the standards. But we achieved still on home compost products by blending with PCL or PBSA. It's of course depending on the type of PLA, but you can really see that the higher amount of PCL, the quicker the degradation starts. So we could also play with the big biodegradation rate. We could tune the biodegradation, which might be an interesting application also for soil applications in agriculture, so that there is a long duration without any degradation, and then afterwards it start degrading. Even with the addition of only 5% PCL, we could obtain a material that was completely home compostable. And a similar approach we used to, together with the University of Pisa, we work together with blending with PBSA, as this is a bio-based material. We show there that also PLA mixed with PBSA can be home compostable. So these are very nice results. Another project we are involved in will be later on by explained more in detail by Amparo. It's Sea Life. The goal was to bring advanced bio-based plastic solutions to the market. Several demonstrators will be produced and developed for land application and for sea. For land, we go for rigid and flexible packaging and also agricultural applications. In sea, we look at deep frozen films, fish crates, oyster mess bags, and fishing nets. In this research project, there's also an important part on policy and standardization, and we are quite involved in standardization work to setting up new test procedures, setting up new standards, and to help them to benefit later on for the EU Commission and for the environment. So we are setting up marine toxicity tests for biodegradable polymers, as they are different for chemicals. You need a degradation phase to allow to have the residuals formed and then to check the toxicity. We also drafted an anaerobic digestion standard with specification. There is a good standard on industrial composting, but it's not existing yet really for biogasification for the treatment of the plastics in an anaerobic digestion plant. So we had made some suggestions, and we did some marine disintegration trials. We compared lab tests with field tests, with real life field testing, together with a partner Seabird. And you can see, we tested several materials: cellulose, cotton, PBS, PBSA, PHBV, and PLA. And the results of one procedure that's developed together with TÜV was quite comparable to the real life conditions for PBS. It's even, we've seen better degradation, disintegration in sea life. Well, there's also an ISO standard, but this is a static test. And we observed after 6 months of material, these films were still visually intact. So that's important to know what is realistic for the environment and how we can better simulate it in the lab. Another project is a MyFi project. Here we have the ambition to provide the textile industry with a new non-woven fabric material made of mycelium fibers. So it's also a natural material, and it should have improved performance and reduced environmental impact in comparison with the current materials. So they have some interesting environmental objectives to reduce the use of chemicals and natural sources, be bio-based, so we have a low carbon footprint, also circular, and we also start materials is waste that they start to let the fungi grow on it. And the option is also to have a biodegradable material at the end. Start material, the mycelium, it's biodegradable, but when you have to obtain for high performance applications like an automobile industry or even fashion industry, you have to do a lot of interaction. So it's decreasing the biodegradation and the compostability. And I think this is the last one I will discuss about as the Unlock project. Here we want to release the potential of feathers to foster circularity in agriculture. So we start with the feathers, waste from the poultry industry. These are keratin-based materials. the objective to have a zero waste to obtain also controlled biodegradability. So that's like for a multifilm, depending on the growth you have on the plants, you have a quicker or a slower degradation. And also final goal is also because the materials are rich in nitrogen, that you can enrich the soil and have a nice fertilized soil. We obviously observed this is biodegradation testing in the soil, that the raw feathers are degrading slowly, but with our treatment, we can have a much faster degradation pattern. Products they want to achieve are multifilm, hydroponic foams, non-woven geotextiles, and forest and seed trays. I think this was the last, but we are involved in many more projects, and we also want to help. We are available for a new project if desired. Thank you.
All right. Good afternoon, everyone. First of all, thank you, Kira, for inviting me and for a bit to the right, to the other side. Okay. It's no, but thank you for allowing me to explain you a little bit more about one of our projects, the REPurpose project, and I will also say a few words on another project, which is GLAUKOS project. First of all, I will explain a little bit on Bio-based Europe pilot plans. For those who are not really familiar with our company, we are a pilot facility located in Belgium, in Ghent, which here are also some colleagues here from Ghent. We are an open access piloting facility focusing on doing process development and upscaling trials in the field of bioprocessing. So, for example, technologies such like fermentation technology, enzymatic technology, biomass pretreatment technologies, also clean chemistry, and so on. For that, we can offer services from lab scale up to pre-commercial scale. As a company, we are also not-for-profit company, working both within European projects, as we are here today, but also as a service to other companies. I will explain you a little bit about our REPurpose project, as it is a fairly new project. It only started a couple of months ago in September last year. I will not be able to present results today, as we are still working on that, but I will explain you about our concept and about the topic where our project is granted in, being the safe and sustainable by design polymeric materials. Here you can see also the overview of the partners, of which some are here as well, nicely spread around Europe. So our concept of REPurpose is actually targeting elastomeric plastics, for example, towards consumer goods, towards automobile application, and towards construction. And to develop these elastomeric compounds, we are starting from waste materials. We're starting from two types of waste materials, namely paper and cardboard waste and plastic waste. The paper and cardboard waste is actually a waste stream that is difficult, let's say, to recycle, or difficult to get back into the loop for paper and cardboard, which has, for the paper and cardboard industry, not a lot of value. However, for companies like us, or fermentation technology, it still has a lot of value, because it's of course cellulosic, so it contains still a lot of glucose. It contains still a lot of fermentable sugars. We can make use of those sugars to create or to synthesize new molecules. So we're using pre-treated paper and cardboard. We are enzymatically hydrolyzing this to glucose and xylose, and we're using the glucose and the xylose to ferment it into new products. Typically, it's about diacids, diols, which we can use then for our polymers. That is one value stream. Second stream is on plastic waste. Typically, it's polyolefinic plastic waste, for example, PET, but can also be PVC and so on. Again, here we are using more or less the same strategy. We will enzymatically depolymerize these plastic waste, again into into the building blocks, and then we will combine
our building blocks that we are getting from the plastic waste, combine it with the building blocks that we are obtaining from our paper and cardboard waste, and make use of that entire pool of those building blocks to create new elastomeric polymers, which we are calling our REP polymers. What's important, or what was important within this call, is that the call is about safe and sustainable by design. So it was very important in the entire concept to, when we are still trying to develop these polymers, and that we take into consideration safe and sustainability. One important aspect of that safe and sustainability is the ability, or we need to create at least the ability that we can recycle these polymers. So to give you an example on that, is that we have a partner within our consortium. It's a Dutch company, Photon Mission, who is a specialist in spectroscopy. So we have implemented here in the project a work package where we want to see, can we, with photospectroscopy technology, can we actually separate, can we detect and separate our new synthesized polymers from the classic streams like PET, PVD, and so on. Because it's important when you have a sorting facility, and that you can specifically sort out your type of polymers. Because if you're not able to sort out, you're not able to recycle. So that is, for example, one aspect that we took into consideration. A second aspect, and Steven also already talked about it, is about biodegradability. It's impossible, of course, to recycle 100% of your raw material. It's impossible to prevent litter, or to prevent polymers to end up in the environment. And because we are making use of also natural building blocks, and the biodegradability at least should be improved from these types of polymers as well. A third aspect on the recyclability in the, let's say, the design of the concept, is that we're making use to create our building blocks with enzymes. Enzymes that are depolymerizing plastics. We intend at least to make use of the same enzymes that are depolymerizing our plastic waste into our building blocks, that if we create new type of polymers, that we can actually reuse those enzymes to also depolymerize again our new type of polymers into those same building blocks, and again being able to resynthesize our polymers, and in that way creating kind of endless loop, and make sure that as much as possible of these building blocks remain in that cycle. So in that way, actually the entire concept was set up always with the safe and sustainability approach, or safe and sustainability by design approach in the back of our heads. It's of course not only on the technology that is important, and there are also several other aspects around the safe and sustainability by design concept that we have included. And for example, our partners from Aimplus are working on an inventory of plastic additives. There's the concept, or maybe to explain a little bit further, the concept as well, by making use of these different types of building blocks that we are having. The idea was also there that if we can play around with the composition, the ratios of all these different types of building blocks, that we can steer the properties of these elastomers. And by able to steer these properties, that we can actually avoid to add any plasticizer or any additives. So that was actually a fourth point, which I should have mentioned in my previous slide. And to come on this slide, so together with that idea, trying to prevent as much as possible to add additives in the plastics, our partner Aimplus is also working and inventorizing the current plastic additives, comparing it with the current ECHA inventory, to see what are still there the gaps, what are the recommendations that we can do to make sure that we can prevent using harmful additives in the future. That is another aspect. We are also strongly involved with our sister project that were granted within the same call, to see from both all the different projects and the different approaches, how we can create how do you call it, an advice, a recommendation strategy to implement a safe and sustainable by design approach for future projects as well. Here on my slide, the best practices in that. Of course, we don't want to make polymers only for ourselves. We want to make real applications, real prototypes. And there we are strongly engaging our end user group. So we have several companies involved where we ask for advice, where we want to, as I mentioned, we are steering these properties of these polymers by changing the composition. So we have actually a very broad spectrum that we can cover. But we of course want to create products that are useful for the companies. And so we have several companies involved, for example, also some big names like Trelleborg, like Bosch, that are helping and advising us in which direction which we need to synthesize these polymers. So if you want to learn a little bit more about our REPurpose project, here is a QR link. You also have the website if you want to know more about Biobased Europe pilot plant as well. Our website is also listed. There we also have an entire list of the projects that we are involved with, more information as well. And if you have any questions, I'm also here and happy to answer them. This was a few slides on REPurpose. I will also explain you a few words on another project, GLAUKOS. This is a project that's a little bit more advanced, has been running already a little bit longer than the REPurpose project. And GLAUKOS, or the name GLAUKOS, actually comes from a Greek god, or a Greek sea god that was actually believed to protect the ocean. And that actually captures what we want to do in the project. In that project, we want to make new type of polymers for textile application. And one of the key topics there is towards fishery equipment, or towards fishing lines, for example, fishing nets and so on. Because what is happening nowadays, that these fishing nets, they remain in the ocean. They are not biodegradable and creating a huge environmental disaster there. So if we can create there a new type of textile, new type of fishing net, that if it ends up again in the ocean, that it's easily biodegradable and that it solves there the environmental problem. But of course, those types of textiles need to have very stringent applications, or stringent specifications, sorry, which makes it also not that easy to develop these polymers. So in short, actually, I will not stand too still within this slide. It has more or less the same concept as within the REPurpose project, where we want to start from a renewable feedstock. We are making use of fermentation technology, microbial fermentation technology, to build again, or to create and synthesize these building blocks. These building blocks are polymerized in the target polymers for these textile applications. Here, what I want to highlight as well is that within the GLAUKOS project, there are several workshops that are being organized, and they have determined several challenges that come with the development of these biodegradable textile polymers. These different types of workshops are divided amongst some main topics. Of course, you have the technical challenge. How do you get to those certain specifications that the fishing nets needs? But it's of course also on, for example, the end of life, which you already had a presentation on. It's about LCA, also a topic that we already talked about. But of course, and even more important maybe as well, is raising awareness, involving all the stakeholders, and making sure that also the public is aware of that. So there are several workshop around this topic, around the different topics being organized, one as well next month. So I warmly invite you to join and to listen. So if you want to know a little bit more about these workshops, here you have the project website. You also have the QR code. And here, if you have any questions on this project particularly, because I'm not following that up, but that's my colleague, Sophie will be very happy to answer any of your questions on that. All right, thank you very much.
Behind the lectern. So thank you, Nico, for the nice presentation about the two projects. Actually, GLAUKOS, we didn't manage to squeeze this into the agenda, but we would be very happy to include him, to include the project in the proceedings and also with a bit more information.
Yeah, sure.
Is there any question related to REPurpose or GLAUKOS to Nico here from the audience? Maybe related to the textiles or no? Okay, I'm looking online. Otherwise, I can break the ice and I can ask you a question, but it's about GLAUKOS actually.
Okay.
And
I will try to answer because I said it's mine.
Yeah, what is interesting is like this multidimensional model. So I saw there are different topics, quite many of them.
Yes.
And I was wondering, like, how do you want to run it over a 4-year project? It's like a huge amount of work and very ambitious. Is there a secret for running all this stuff? We need to learn.
There is no secret to reveal, and I think the challenges are challenges that I think every one of us here face, that every project face when developing new type of polymers and new type of products. It is always a technical challenge. How do you get to the specifications that you need? Is my new material indeed biodegradable? Is it sufficient enough? You also touched already on the topic today about regulatory, the single-use plastic, the single-use directive. So I think many of these challenges are probably very similar to all the projects, and these challenges have been determined for the project itself, for this application. But within the workshops that they are organizing, they want to, let's say, open that discussion also
open
to other, open that dialogue to other projects and other stakeholders as well, to see how we can, for new projects, for further development, how we can further.
The kind of involvement that you have at this level of these workshops, is it from the industry, from research, from everybody's welcome, or how do you want to...
Sure, yeah, everybody is welcome, and indeed not only research, but especially I would say also companies, and the ideas are very welcome.
Okay, so maybe this is like an open call as well that we can share with our networks, because each of us is representing at least 3 or 4 projects.
Exactly.
Maybe this is, if you can point us to some resources, maybe we can put this also in your slides. Yeah. I think it would be great. So that I will do that. Okay, excellent.
All right.
There is a question from Salvatore online. Can you say something about the class of polymers developed from the elastomers, polyesters, polyamide, etc.? Thanks.
So today I cannot disclose any details of these polymers. I can only tell you that it is about elastomeric compounds. So they are polyester-like compounds, but I cannot tell you a little bit more detail.
Closer to the microphone. Closer. They didn't get it.
Yeah, okay. Then I will repeat. So within the REPurpose project, we're targeting elastomeric polymers. As I said, because the project is still in full development, and together with our partners, we cannot disclose any details on that. But as I mentioned, we are making use of diacids, diols, so it's our polyester type of.
So I think, Salvatore, you need to be happy with this reply, and maybe you can follow up on what's happening later on this project.
If you have a specific, more detailed question, you can always email me.
Yeah. Yes, and your name is in the proceedings as well.
Exactly.
In the book of
and then I can see what I can also together with the partners.
Okay. Message has arrived. Thank you. Okay, thank you, Nico. Very nice.
Welcome.
Thanks a lot.